A silent bubble could rewrite the laws of physics at light speed. That's the terrifying premise of vacuum decay. It's a theoretical phenomenon where our universe might delete itself without warning. You can understand the scientific mechanisms behind this ultimate cosmic erasure, and what it reveals about the fragile foundation of our reality. We can explore how a single quantum event in deep space could trigger an unstoppable wave of new physics, whether the universe we know is built on a foundation of sand. What does it mean to live in a cosmos that could, in principle, simply change its mind? To understand how a bubble could erase everything, you have to know what the universe is made of. Look at the space around you, it feels empty. But physics says that emptiness isn't real. Every cubic centimeter of space, everywhere, is filled with something called the Higgs field. It's not a metaphor, it's a real thing. Its job is simple but huge. The Higgs field gives particles their mass. Without it, every particle would move at light speed. Weightless, nothing could bind. No atoms, no chemistry, no stars, no us. You can think of it like a cosmic molasses, a gentle resistance. An electron moving through it gains a little heft. A top quark gets bogged down a lot. The strength of this field, its value at every point, isn't random. It's a number that sets the rules. It decides particle masses. That dictates the forces, the stability of atoms, the laws of physics. This value is the bedrock of our reality. But then the mystery gets deeper. What if our universe, with this Higgs value, isn't at the absolute bottom? Imagine a ball resting in a small dip on a hillside. It's stable for now. Physicists call that a false vacuum, a metastable state. It feels like the lowest point, but a much deeper valley is hidden below. Our cosmos might be that ball. We're in a precarious valley, a local minimum. It feels permanent, but it might be temporary. The true lowest state, the global minimum, could be completely different. In that true vacuum, the Higgs field would have a different value. The cosmic molasses would be a different thickness, and that change would rewrite the rulebook. The constants for life would vanish. The forces holding your atoms together would stop working as they do. That sets up a terrifying possibility. Our universe in its current form might not be the final answer. It might just be one arrangement, and not even the most stable one. All it would take is one quantum nudge, one tiny event with enough energy to push the ball out of our little dip, and send it rolling down the hill toward its true and utterly alien resting place. Deep in the cold dark between the stars, there's a kind of whisper. A quantum one, and it could be how everything ends, because the universe isn't perfectly still. At the smallest scales, empty space isn't empty, it seethes. Particles wink in and out of existence. That's the quantum foam. It's this constant background hum of possibility. And in that sea of fluctuations, something exceptionally rare could happen. A tiny region of space, no bigger than a subatomic particle, might get a sudden surge of energy, a colossal one, from the quantum foam itself. It's like a single, incredibly tense point on the surface of a balloon finally giving way. And that energy would be enough to do the impossible. It would push the Higgs field in that spot up and over the barrier that separates our stable valley from a deeper one. That's called quantum tunneling. The field doesn't climb the hill, it cheats. It appears on the other side like magic. And in that instant, a new universe is born. A microscopic bubble of what physicists call the true vacuum. It nucleates right there in the void. Inside that bubble, the Higgs field snaps. It goes instantly to its absolute lowest possible energy state. And the rules change immediately. The thickness of the cosmic molasses is now different. The constants that govern forces, they are rewritten. The delicate balance that lets protons and electrons form stable atoms, it just breaks. Inside this new region, matter as we know it can't exist. It's a zone of alien physics, fundamentally hostile, irreversibly hostile, to every structure that makes up our world. From galaxies down to DNA, and this bubble, this pinprick of a new reality, it wouldn't sit still. The clock starts when that bubble forms, it's not slow. The boundary, this wall between the old universe and the new one, it's under pressure you can't really imagine. That energy difference between our false vacuum and the true, deeper one. It's not just an equation, it's a force, a constant, colossal shove. That energy gap, it's like an engine with infinite fuel. It pushes the bubble's surface outward in every direction at once. And the chilling part is the wall itself. It isn't matter, it's not a physical thing you could touch, it's a front. A wave of redefinition, moving through the quantum fields that are space. And since those fields are what let cause and effect happen, the wave isn't bound by the rules of stuff. It doesn't push against anything. It just rewrites the rules as it goes. And the new rules let it move at the universe's speed limit, the speed of light. Picture a single, flawless sheet of ice on a vast lake. Then a crack appears. Not from weight, but because the ice itself decides to become water. The moment it cracks, the tension releases. That fracture races outward. It doesn't ask. It doesn't slow. It just goes, transforming solid to liquid instantly. The vacuum decay bubble is that crack, but in the fabric of reality, and its speed, there's no earthly comparison. At light speed, it crosses the entire orbit of Pluto in just over 8 hours. From a microscopic speck, it becomes a sphere light years across in a cosmic blink. There's no outrunning it. Nothing with mass can travel faster. No warning could reach you faster than it does. You'd see the wall coming at the very moment it arrived. A flash of impossible light on the horizon, and then a new set of physical laws. The old universe, our universe, wouldn't be destroyed in an explosion. It would just be replaced, erased by a growing sphere of absolute change. So the question isn't just if our cosmos is unstable. It's whether that trigger has already happened. Somewhere in the vast dark, and its silent, luminous wall is already on its way. That flash on the horizon is the last thing you'd ever see, but what comes after isn't fire. It's not ruin, it's something deeper, more final. Inside that sphere, the universe isn't damaged, it's been edited. The source code of physics gets overwritten. The Higgs field drops to its true vacuum, a new, lower value, like cosmic molasses suddenly becoming thinner, or maybe impossibly thick. And that one change ripples through everything. The constants that were fixed, the fine structure constant, the forces in a nucleus, they become different numbers. The balance that built stars over billions of years just snaps. In this new reality, protons might not be stable anymore. They could just fall apart. The bonds between quarks could dissolve. Every atom, everywhere. The hydrogen in a nebula, the carbon in your hand, it all ceases to be. There's no explosion, no shockwave. A star is a fusion engine one moment, the next it's a cloud. Electrons and quarks, drifting under laws they don't recognize. A brain isn't crushed, it's unmade. Its structure depends on chemistry, and chemistry needs atoms to hold their shape. When the atoms vanish, the structure goes with it. Everything it contained. The bubble's interior isn't a place of destruction. It's an absence of the rules that allowed our kind of complexity. It becomes a barren, elemental soup, governed by a new physics, a simpler one, a blank page where an entire epoch was just erased. So it's not the end of the world. It's the end of the operating system, a silent, luminous upgrade to a version of reality where we are no longer compatible, where everything we've ever known no longer runs. The idea didn't arrive in a dream. It came from chalkboards, from equations. This was the late 70s. A physicist, Sidney Coleman, and his colleague Frank DeLucia, they were working on a question. What happens if a quantum field, the kind that fills everything, finds a lower energy state? They used the math for quantum tunneling, that process where particles slip through barriers. They applied it to the whole universe. Their papers described it. A single region of space could tunnel into a new state. It would make a bubble, and that bubble would expand. At the speed of light. This wasn't a prophecy, it was just the logic of quantum field theory, followed to its end. Their work built the mathematical skeleton for it. Turned a philosophical question into something you could calculate. Inside our best models, For a long time it was a footnote, a theoretical one. Then in 2012, an experiment changed things. The Large Hadron Collider at CERN, they found the Higgs boson, a huge triumph. It confirmed the Higgs field exists. That field is what gives particles mass. But in physics, answers lead to more questions. Finding the Higgs boson was like finding one piece of a much larger landscape. It told us the field is there, but not the exact shape of its potential. Whether the valley we're in is the deepest one, or if we're on a slope. The data from CERN gave numbers, masses, energies, interaction strengths. Physicists put those numbers into the equations. The answers varied. Some calculations suggested our universe might be metastable. That false vacuum, precarious. The discovery meant we weren't talking about abstraction anymore. We were measuring the actual ingredients of our cosmic stability. Or the lack of it. That arc is important. It means vacuum decay isn't science fiction. It's a serious implication, from where quantum theory meets experimental data. It's a shadow, cast by the light of our own understanding. That shape is the Higgs potential. It's a landscape, hills and valleys. The depth is energy, lower is more stable. Our whole universe, all of it, is a single point on that map. We're in one valley. The Higgs field has a value here which gives us the physics we know. This spot feels solid, permanent. It's the only reality we've ever known, but the map might show something else. Our valley might not be the deepest. There could be a chasm somewhere else, a global minimum, a true vacuum valley, lower and infinitely more stable than ours. We're in what's called a false vacuum. A local minimum, stable for now, like a ball resting in a small dip on a hillside. It would take energy to push it out. But if it ever gets out, it rolls all the way down. Everything depends on the barrier between these valleys. How high is the hill between our dip and that deeper chasm? And how wide? If the hill is enormously high and very wide, we're safe. The quantum fluctuations in empty space could never muster the energy to push the ball over. But if the hill is lower or narrower, then it becomes probability. Not certainty, but chance. Over enough time, in a vast enough universe, a quantum event with just the right energy could tunnel through. It wouldn't climb over. It would cheat, appear on the other side, and that event creates the bubble. This is where data from particle colliders becomes a crystal ball. Physicists take the masses of particles, the Higgs boson, the top quark, measured with incredible precision, and feed them into the equations for this potential landscape. They're using a subatomic blueprint to survey the cosmic terrain. And the latest surveys are inconclusive but thought-provoking. The numbers don't point to a flat, featureless plane of absolute stability. They suggest a landscape with more interesting topography. Many calculations show our valley is metastable. It could last for billions upon billions of years. Far longer than the current age of the universe, but it might not last forever. The mathematical signature of our cosmos could be a temporary arrangement. A beautiful, complex, but fleeting configuration of the fields that make up reality. This mathematical uncertainty creates a duality. For scientists, it's a thrilling puzzle. A clue written into the most fundamental constants. It drives the search for new particles, for new physics that could tilt the calculation toward permanent stability. But for the human spirit, it whispers a different question. It introduces a timescale of existential patience, a countdown so long it dwarfs all of human history, yet one that is theoretically finite. Our universe might not be an eternal stage, but a temporary set. And the mathematics we use to understand it is the same mathematics that hints at its eventual, quiet closing night. That mathematical uncertainty isn't just empty space. It's a frontier, and right at its edge, we have the most precise measurements we've ever made. Deep underground, in a tunnel between Switzerland and France, the Large Hadron Collider smashes protons together almost at light speed. Those collisions recreate, for just an instant, conditions from the universe's very beginning. And from all that chaos, detectors as big as cathedrals find the traces of fundamental particles. Two of them are central to this: the Higgs boson, which is tied to the field that gives other particles mass, and the top quark, which is the heaviest particle we know. Their exact masses aren't just entries in a chart. They're the key coordinates for charting that landscape of cosmic stability. When you take these measured masses and put them into the standard model equations, you get a provocative result. The math suggests the valley our universe is in might not be the deepest one possible. It points to a metastable state, a false vacuum. The numbers, as they are now, indicate a universe that's stable for the moment, but not for all time. Given enough time, in principle, a quantum event could push it over. That's where the headline comes from. The raw data implies our cosmos is on shaky ground. But science isn't just about the raw data. It's about grasping the margins of error, the limits of what we know. And here, the story turns to profound caution. The top quark's mass is especially hard to pin down with total precision. Its measurement has a margin of error. That uncertainty isn't minor. It's a wide corridor of possibility. And inside that corridor, the fate of the universe changes completely. Move the top quark's mass just slightly one direction, and the calculations could show our vacuum is actually perfectly stable, sitting in the true deepest valley. Move it the other way, and the signal for metastability gets stronger. Then there's the most important caveat. These calculations are done within the standard model. It's our best description of the particle world, but we know it's incomplete. It doesn't include gravity. It doesn't explain dark matter. There are almost certainly new particles, new forces, new fields we haven't found yet. Any one of those undiscovered pieces could totally reshape the potential landscape. It could show there are hidden supports under our valley, making it permanently secure. Finding a new particle tomorrow could turn this whole metastability warning into a footnote. So what we're left with is a duality. On one side, a legitimate, data-driven hint that the fundamental state of our universe could be temporary. It's a staggering insight that comes from our most advanced science. On the other side, a humble admission of the vast unknowns that still surround us. The risk, in the strictest theoretical sense, isn't zero, but it's also nowhere near a confirmed fate. It's a possibility written in faint pencil, not carved in stone. It's less a prophecy and more a question, one of the most profound questions we can ask. And chasing that answer is what pushes the next great leap in understanding reality. Our calculations can point toward instability, but the universe we see doesn't match that. It's still here, it's not just stable, it's lasted almost 14 billion years. That length of time is a clue. It means there might be safeguards already built in. The first evidence is that we exist. In the very beginning, the universe went through cosmic inflation. Space expanded faster than light. It stretched tiny quantum fluctuations into the seeds for galaxies. The energy back then was far higher than anything we can create now. Higher than any particle collider. If the vacuum was truly fragile, that would have been the moment. The violence of inflation would have had enough energy to push the Higgs field over any barrier. It would have triggered decay instantly. The universe would have ended before it began. The fact that it didn't is a strong hint. It means the barrier protecting our valley is higher or wider than our simplest estimates. The universe already passed its most extreme stress test. Then there's what we don't know. Our equations for vacuum stability have a limit. They work inside the standard model, but that model doesn't include gravity. When you get to the Planck scale where quantum effects and gravity are both powerful, our math breaks down. It's like using a weather map to forecast inside a black hole. Quantum gravity in that realm could reshape the whole energy landscape. It might act as a stabilizer, reinforcing the walls of our valley in ways our theories can't describe yet. The true nature of the vacuum might need a theory of everything. We don't have that. So the metastability warning comes with an asterisk. It's pending further discovery. There's also a strange form of protection from the universe's current behavior. We live in a time of accelerated expansion, driven by dark energy. Space between galaxies is stretching apart faster and faster. That creates a scenario. Even if a true vacuum bubble formed somewhere far away, the space between it and us might be expanding faster than the bubble can grow. The bubble wall moves at light speed. But if the space it needs to cross is being created even faster, it could never make the journey. The decay front would chase a horizon receding faster than light. The threat gets quarantined, isolated in a pocket of space that can never reach us. It's a cosmic fail-safe. The same force pulling the universe apart also shields it from undoing. So we're left with this tension between the unsettling results of our most precise equations and the enduring stability of the cosmos we observe. It's not a contradiction. It's a dialogue between theory and observation, pushing toward a deeper truth. That enduring stability brings up a deeper puzzle. If the universe is so precarious, why does it feel so solid? Why are we even here to think about it? It's not just a scientific question. It's a kind of cosmic survivor's bias, and it points to an idea called the Anthropic Principle. In its simplest form, it's a tautology. We can only observe a universe capable of producing observers. We are a product of the cosmos. So the cosmos we're in must have the right conditions over vast stretches of time for stars and planets and chemistry and life. A universe that decayed into a true vacuum instantly would have no one in it to wonder. By the very fact we are here asking, we are guaranteed to be in a region of reality that's stayed stable for billions of years. Our existence is the evidence that reframes everything. It moves vacuum decay from a looming threat to a kind of cosmological filter. Imagine not one universe, but a multiverse. A vast landscape of different domains. In that picture, different regions could have settled into different vacuum states early on. Some fell into deep, barren true vacuums right away. Others, like ours, landed in a higher energy false vacuum. A metastable state that has, against the odds, lasted long enough for galaxies and life. We don't live in the average region. We live in the exceptionally rare, long-lived neighborhood where observation is possible. The unsettling math of vacuum decay doesn't necessarily mean our bubble is about to pop. It might just explain why we find ourselves in this bubble, and not in the countless others where the story ended before it began. It becomes a reason for our existence, not just a threat. The silence of the cosmos, the absence of other civilizations, might even find an explanation here. Maybe most cosmic real estate is fundamentally uninhabitable, eternal, quiet domains of true vacuum where complexity is impossible. We are the lucky ones on a temporary island of stability in a sea of silent physics. This perspective doesn't eliminate the theoretical risk, but it changes the emotional weight. It suggests we are not passengers on a ship doomed to sink, but explorers who have, against astronomical odds, found a vessel that has sailed for eons and shows every sign of continuing. Our worry is a testament to our good fortune. We are here to contemplate the abyss precisely because, so far, it has kept its distance. This idea of cosmic luck opens up something even bigger. If our universe is a rare, stable bubble, then what's outside it? Modern cosmology has an answer. A multiverse. It's not really a theory in the traditional sense. It's more a prediction that comes out of our best models for cosmic inflation. In that picture, all of space is like a frothing, eternal sea. New universes keep bubbling up. Each one gets its own random set of physical constants. Our whole cosmos, with all its galaxies, could just be one bubble in an infinite foam. And here, the scary idea of vacuum decay changes completely. It stops being a universal delete button. It becomes something else, a way for the cosmos to reproduce. Think about that true vacuum bubble again, the one that rewrites physics as it expands. In the multiverse framework, that bubble isn't ending a story. It's starting a new one. From the outside, from the perspective of the parent universe, it looks like decay. A region changes state and grows, but from inside the new bubble, it's a big bang. A whole new universe, born with a different set of fundamental rules. The moment the Higgs field tunnels to its new value, it releases a huge amount of energy. That energy fuels a burst of inflation inside the bubble, stretching it into a vast, self-contained cosmos, one that might be forever cut off from the universe that spawned it. In this view, our own universe could have begun this way, as a quantum fluctuation, a bubble of new vacuum in some other, older reality. Our laws of physics aren't written in stone. They're frozen accidents, the random result of which valley our particular bubble landed in when it inflated. This is the core of eternal inflation models. They suggest that once inflation starts in some region, it never truly stops. It becomes a perpetual engine of creation. Most of this inflating space just keeps expanding forever. But here and there, quantum events cause pockets to tunnel out, to drop into a lower energy vacuum state. And each of those pockets becomes a separate universe like ours. In this grand landscape, vacuum decay events aren't rare catastrophes. They're the most common thing in existence. They're how the multiverse breathes, how it diversifies. Each new bubble is an experiment in physics. The vast majority of these experiments produce barren universes, ones where the constants don't allow for atoms or stars or complexity. But given an infinite number of tries, a few will, by sheer chance, land in a valley like ours, stable enough and with the right numbers for galaxies and life to form. So the potential for our own vacuum to decay is part of a much larger tapestry. It puts the possible end of our local reality inside a cyclical story of cosmic birth and destruction. Our universe might one day spawn new ones through the same quantum process. And if it does, it won't be an erasure. It will be a legacy, a branching of the cosmic tree. The silence we fear might just be the distance between branches. This reframes everything. The fragility in our equations isn't a flaw, it might be a feature. The very mechanism that allows for infinite variety and ultimately, for our own improbable existence. We are not just passengers on a temporary vessel. We are the temporary vessel itself, and we may carry within us the seed for realities yet to come. That legacy of creation has a chilling footnote. If our bubble ever spawned a new one, or if one was coming toward us from somewhere else, we'd have no warning. None. The detection problem is absolute. The bubble wall moves at light speed, so it carries its own announcement. No signal can outrun it. No particle, no flash of radiation. The first sign wouldn't be a distant alarm. It would be the event itself. A silent, invisible wall of rewritten physics sweeping over us in an instant. One moment, the universe works by the rules that built planets and people. The next, those rules are just gone, replaced by an alien set. There's no approaching rumble. No growing light in the sky you could watch for hours. It would be as sudden as flipping a light switch. The horizon would simply change, and with it, everything. You can picture a vast, dark plain at night. A single, perfectly straight line of impossible brilliance appears on the edge of sight. It's not coming toward you. It's already there, because the light from its approach is the same light that brings its presence. You see it the exact moment it reaches you. There's no interval for thought, for reaction, for goodbye. It's a full stop written into the laws of causality. That makes the idea uniquely terrifying in a cosmic sense. Most existential threats, like an asteroid or a nearby supernova, offer at least some possibility of detection beforehand. We could see them coming even if we couldn't stop them. Vacuum decay offers no such courtesy. Its physics forbids a heads-up. There's only one remote, theoretical way we might ever know such an event was possible. And it's a paradox. If we could point our most powerful telescopes at distant galaxies and see a patterned wave of transformation sweeping across the universe, seeing galaxies not explode, but simply cease to shine in a coordinated, expanding sphere, that would be a monumental discovery. It would confirm vacuum decay is real, but it would also confirm the wave was already ancient and likely already upon us. The image of that distant galaxy winking out would have traveled at light speed, just as the decay front itself does. If we see it a billion light-years away, It means the event happened a billion years ago, and the sphere of new reality has been expanding for all that time. It could be alarmingly close. Such an observation would be the ultimate confirmation of a doom already en route. It would offer no chance of escape, no possibility of response. Cosmic knowledge paired with absolute powerlessness. That transforms the detection dilemma from a practical problem into a philosophical one. It asks a profound question about the nature of knowledge and existence in a potentially unstable universe. Is it better to live in ignorance of such a shadow, or to possess the terrible certainty that a line of erasure is crossing the cosmos, with our name written somewhere on its path? The silence of our telescopes, the absence of such a patterned wave, is therefore our only comfort. It's not proof that decay cannot happen, but it is evidence that if it can, it hasn't happened yet in our galactic neighborhood. For now, the night sky remains a tapestry of consistent physics, a silent testament to the enduring, if temporary, stability of our little bubble in the multiverse. The silence in our telescope sits something fiction almost never gives us. In stories, the end of the universe is never quiet. It's always a spectacle. A wave of fire, a swarm, a visible crack in the sky. Vacuum decay in popular culture follows that rule. In the three-body problem, there's a weapon called a dual-vector foil. It reduces a star system from 3 dimensions to 2. That's not exactly vacuum decay, but it has that same finality. A rewrite of physics that spreads at light speed, leaving a flat, lifeless artwork behind. It's a conscious weapon, a narrative choice that gives the catastrophe a sender, a purpose, a visible result. Doctor Who does something similar. Entities like the void, waves of reality collapse. They're shown as a storm of energy, a creeping nothingness you can watch approach. These are brilliant stories. They make the unimaginable visible. They give it an edge you can see coming, a sound. They turn an abstract equation into a monster you can run from, even if you can't outrun it. That's where science fiction and science fact diverge. The creative liberty makes for drama, but it obscures the real thing. The scientific version of vacuum decay has no visible wavefront. No roaring silence, no intent. If a bubble of true vacuum were expanding toward Earth, the wall would just be a boundary of pure law. On one side, the universe works as it always has. On the other, it works differently. There's no flashy energy to see, because all the energy is used in the transition itself, in rewriting the constants. You wouldn't see a wall of light. You'd see the universe ahead behaving normally, until the exact coordinate where the field redefined itself passed over you. Then your instruments, your eyes, your atoms would cease to function under the old rules. The change is instantaneous, total. It's not an explosion that destroys structures. It's a change in the instruction set that makes those structures impossible. Fiction gives us a monster to fear. Science gives us a silent edit. One is terrifying in a familiar, cinematic way. The other is unsettling in a philosophical, absolute way. It's the difference between watching a building collapse and realizing the ground it was built on never existed. That contrast is crucial. It separates sensationalized doom from a subtler, existential insight. The pop culture versions usually give a warning. A character sees the wave coming. They have a moment to understand. The scientific version offers no such moment. Its arrival is its announcement. By dramatizing the event, fiction provides a false comfort, the comfort of spectacle of a defined threat. The scientific truth removes that comfort. It replaces it with a quiet, statistical possibility. It says if the cosmos were to change its mind, we wouldn't get a story out of it. We would simply cease to be part of the narrative. That's not a flaw in storytelling. It's a necessary translation for minds that crave pattern and agency. But recognizing the difference sharpens things. It means the real awe of vacuum decay isn't in a fiery Hollywood ending. It's in the quiet realization that the laws of nature, which feel so permanent, might carry within them the seed of their own quiet revision. That our entire reality is built not on bedrock, but on a stable arrangement that has so far favored our existence, Fiction makes us fear an event. Science invites us to contemplate a condition, the fragile, precious, and possibly temporary state of everything we know. There's this philosophical weight. And it leads to a difficult question. Should we even be looking? Is there a danger in probing the stability of reality itself? On one side, this is the ultimate human project. To understand where we are, what we're made of, the true nature of the cosmos that gave us life. That pursuit of knowledge is what separates us. It's the pinnacle of curiosity. To turn away from it would be to abandon a fundamental part of who we are. We'd be choosing to live in ignorance about the foundation of our own existence. And that seems like a profound surrender. But the other side of the argument carries a whisper, a chilling one. What if the act of looking changes what we see? Or worse, what if it triggers the very thing we fear? The concern isn't about telescopes. It's about particle colliders. In theory, if you concentrate enough energy in one tiny point of space, you could create the conditions for a quantum event that doesn't normally happen. You could provide the nudge. The fear is that a high-energy experiment, by smashing particles together with unprecedented force, might momentarily create a state that lowers the energy barrier. It might make that quantum tunneling event not just possible, but probable. That's the core of the ethical debate. Does pushing the frontiers of knowledge come with an existential responsibility we're not equipped to handle? But the scale here is crucial. The energies needed to even approach that hypothetical threshold are astronomical. They are far, far beyond anything our most powerful machines can produce. The Large Hadron Collider operates at energies trillions of times lower than what would be required to pose any conceivable risk. We're not playing with matches next to a cosmic powder keg. We're, at most, carefully studying a single grain of sand from a beach that stretches beyond the horizon. The fears, while understandable from a narrative standpoint, aren't grounded in our current or foreseeable technological capabilities. Yet the debate itself is valuable. It forces a conversation about the weight of discovery. It reminds us that knowledge isn't free of context. Our quest to map the fundamental forces carries with it a sobering awareness of the power those forces hold. This isn't about stopping science. It's about conducting it with open eyes and a humble recognition of the scale of the universe we're trying to understand. The very fact we can have this discussion, weighing the risks and rewards of pure inquiry, is a testament to how far we've come. We are the universe questioning its own stability. And in that act of questioning, we find not just danger, but a profound and defining purpose. That philosophical weight has a timeline, a kind of cosmic clock. And its hands move so slowly they might as well be frozen. When you run the numbers for vacuum decay, you don't get a countdown. You get a number that's just too large to really grasp. The half-life of our false vacuum, the time by which there's a 50% chance it's tunneled, it isn't in billions of years. It's in powers of 10. The estimates usually go from 10 to the 100th years, to numbers even bigger than that. 10 to the 100th. That's a 1 with 100 zeros after it. A Googol, and our universe is only about 10 to the 10th years old. A 1 with 10 zeros, so the expected time until a decay is longer by a factor of a 1 with 90 zeros. It's to the age of our universe what the age of our universe is to the briefest instant you can think of. Or take a different scale. Compress the whole history of the cosmos into a single year. The Big Bang at midnight on January 1st. Our solar system forms in early September. All of human history fits into the last few seconds of December 31st. On that scale, the time until a vacuum decay might not come for another trillion of those cosmic years. Or a trillion. It makes the life of a star look like a blink. It makes the death of the last black hole seem like something happening soon. And that time frame does something. It turns the theoretical risk from a threat into an abstraction. For any human purpose, it's zero. You're more likely to be hit by a meteorite that just assembles itself from dust in your yard tomorrow. More likely than the sun turning into a cube of gold. The perspective is one of cosmic patience. An almost absurd patience, The universe seems to be in a state of profound stability. The mechanisms that could undo it are so slow, so choked by probability, that they pose no real danger to anything that will ever exist here. Stars will burn out. Galaxies will drift apart. The era of light will fade into dark expansion. And through all that deep time, the vacuum we're in will almost certainly stay just as it is. It's not a guarantee of eternal safety, but it is a reassurance, written in math. It says the foundation of reality, maybe not the deepest one possible, is solid enough to outlast every chapter of the story it started. The ultimate cosmic clock isn't ticking down to an end. It's measuring an endurance so vast that from where we are, it looks the same as forever. That endurance, measured in Googol of years, puts our own cosmic lifespan in a strange new light. It's a scale so vast it invites a different question. If not vacuum decay, then what? How else might the story of everything finally close? The universe is full of potential endings, each with its own flavor of finality. And by comparing them, the true nature of vacuum decay comes into sharpest focus. The most widely accepted forecast is heat death. It's not a dramatic explosion. It's a slow, relentless fade. The universe keeps expanding, driven by dark energy. Over trillions of years, the last stars burn out. Galaxies drift apart into an ever-cooling darkness. Black holes, over incomprehensible timescales, evaporate through Hawking radiation. Eventually, all that's left is a thin, uniform sea of particles and radiation, spread so thinly that no two particles ever meet again. The temperature approaches absolute zero. All useful energy is gone, no work can be done, no structure can form. It's a quiet, eternal stillness governed by the same physics we have today. It's an end of activity, not of existence. Then there's the big crunch, a kind of mirror image. This scenario requires the expansion of the universe to slow, stop, and reverse. All matter and energy come rushing back together in a cataclysmic collapse, a reverse of the Big Bang. It would be a fiery, violent conclusion, but again, one happening under known laws. The universe would end in a singularity of infinite density, much like how it began. A more modern idea is the Big Rip. Here, dark energy doesn't just push galaxies apart. It grows stronger over time. Eventually, its repulsive force overcomes every binding force in nature. First, galaxy clusters are torn apart, then individual galaxies, then solar systems. In the final moments, planets are ripped from their stars, molecules are pulled apart, atoms are shredded, even atomic nuclei are torn asunder. It's a violent, dramatic end, but still one where the fundamental forces are fighting a losing battle against a known, if mysterious, component of our universe. Now place vacuum decay among these. Its defining characteristic isn't violence or slowness, it's replacement. In heat death, the laws of physics remain, presiding over a frozen, dark eternity. In a Big Rip, gravity and electromagnetism are overpowered, but they still exist. Vacuum decay is different. It doesn't destroy things under the old rules. It replaces the rulebook itself. One moment you have atoms, chemistry, and the forces we know. The next, you have a new, alien physics where those structures are impossible. It's an erasure of context, not just content. That's what makes it philosophically unique and uniquely terrifying. It's not the end of the world. It's the end of the framework that made a world possible. In terms of likelihood, current cosmology strongly favors a version of heat death. Our measurements of dark energy point to a universe that will expand forever, growing colder and darker. The Big Crunch and Big Rip are considered less probable given current data. And vacuum decay. Its probability is buried in those Googol-Year timescales and theoretical uncertainties. It is, by any practical measure, the least likely of these endings to occur within any meaningful time frame. But probability and impact are two different things. A car crash is far more likely than a planet-killing asteroid impact, but the scale of consequence is incomparable. So vacuum decay stands apart in the gallery of cosmic doom. It is not the most probable end. It is the most absolute, the most alien, It represents a failure not of structures within the universe, but of the universe's own foundational state. This comparison does something important. It contextualizes the fear. It moves vacuum decay from a looming, immediate threat in the popular imagination to what it truly is: a profound insight into the potential fragility of physical law. A reminder that our reality, for all its apparent solidity, might be a temporary arrangement in a much larger, stranger multiverse. The true terror isn't that it will happen. The awe is in realizing that, according to our best math, it could. And in that possibility, we glimpse the breathtaking, humbling contingency of everything we are and everything we see. The most mysterious ingredient is dark energy, that force making the universe expand faster. It's pushing galaxies apart, but it might be telling us something about the vacuum, the energy of empty space, and that connects it to the Higgs field, to the question of stability. They're both about the vacuum. One gives particles mass. The other drives the acceleration. Some ideas say they're not separate puzzles. They're two pieces of the same one. The value we measure for dark energy is incredibly small. But it's not zero, and that precise number could act like a dial. Tweaking it could change the landscape of the Higgs potential, make our valley deeper and more stable, or shallower and more precarious. So the fate of the vacuum isn't isolated. It's part of a balance sheet, where dark energy's tiny number is a crucial term in the equation for everything. This leads to a possibility. What if the acceleration isn't a constant? What if it's a process, a very, very slow one, like a phase transition, water turning to ice, but stretched across the entire life of the cosmos? Instead of a sudden bubble popping at light speed, the Higgs field could be shifting gradually, a slow roll toward its true vacuum. The energy released by this incredibly sluggish transition could be what we measure as dark energy. The force tearing the universe apart might be a symptom. The vacuum quietly finding a new state. It would mean the two greatest mysteries are one. The accelerating expansion isn't just happening within our universe. It could be the universe itself changing. The timescales are almost impossible to grasp. A transition over tens of billions of years is, for all practical purposes, permanent. We would never see its conclusion, but mathematically it reframes our epoch. We aren't in a static cosmos with a strange force. We might be living in the middle of a cosmic metamorphosis. A transformation so slow that from our brief vantage point, it looks like a simple, relentless push. This idea doesn't spell immediate doom. It could imply the opposite. A slow roll transition suggests stability, not a sudden collapse. The universe is changing its state in a controlled, gradual manner. There may be no catastrophic bubble. Because the entire cosmos is shifting together in unison, the danger of a light-speed erasure could be off the table, replaced by this grand glacial evolution. Our fate would be tied not to a quantum accident, but to the destiny of this slow roll. Where is it heading? Toward a colder, darker version of our current physics? Or toward an entirely new set of laws? A future so distant it makes stars look ephemeral. The acceleration we measure today would be just a single data point on a curve that spans eons. A clue that we are not at the end of cosmic history, but perhaps still somewhere in its long, slow middle. The pace of cosmic change is so slow. And then there's this much faster, human fear. Could we accidentally trigger the end ourselves? The idea that a machine, a particle collider, might create a bubble that deletes reality. It's a powerful modern anxiety. It feels plausible, in a world where our technology keeps unlocking new forces, unpredictable forces. But the physics here isn't just reassuring, it's definitive. The energy you would need to probe the Higgs potential deeply enough to even approach that theoretical barrier is astronomical. We're talking about the Planck energy scale. That's the level where gravity becomes as strong as the other fundamental forces, where our current laws of physics break down entirely. To reach it, you'd need to concentrate over 10 quadrillion times more energy into a collision than the Large Hadron Collider's most powerful smash. That's a 1 with 16 zeros after it. For perspective, the entire planet Earth, converted entirely into pure energy via Einstein's equation, would still fall short, by a colossal margin. The only time such energies existed naturally was in the first instance after the Big Bang itself. Our most advanced machines aren't just small in comparison. In the cosmic sense, they're utterly insignificant. They're gentle probes in a shallow pond. Not drills aimed at the foundation of reality. The fear of a man-made vacuum decay event comes from narrative, not from the hard numbers of particle physics. It confuses the map with the territory. Our equations can describe a landscape of staggering energy, of potential instability. But our technology exists in a tiny, safe valley within that landscape. We're sketching the blueprints of a continent while standing safely on its most stable shore. And that offers a profound kind of reassurance. The quest to understand the universe's fundamental nature doesn't carry an existential risk of accidentally ending it. Our curiosity isn't a loaded gun pointed at the cosmos. It's a humble light, illuminating just how vast the stage of our existence is, how stable and how patiently enduring. The safety we feel comes from the sheer scale of the energy involved. But that central idea, a whole system flipping to a new state, we see that all the time. In materials, it's a phase transition, and it's the right analogy to make vacuum decay feel real. Take a bottle of very pure water. You can cool it well below freezing and it stays liquid. It's supercooled, that's a metastable state. The water molecules want to be ice, a lower energy, more stable arrangement, but they need a start, a nucleation site. A speck of dust or a vibration. Once that happens, the change doesn't creep, it races. Ice crystals shoot through the liquid instantly, locking the whole volume into a new, solid state. The system finds its true ground state, or a simple bar magnet. At room temperature, its tiny atomic magnets are aligned, that creates a north and south pole. Heat it up. As the temperature passes a specific point, the Curie point, something happens. The thermal energy overwhelms the forces keeping the atoms aligned. The magnetization vanishes. The whole material transitions from an ordered magnetic state to a disordered, non-magnetic one. It's a spontaneous symmetry breaking, undone by energy. Cool it back down and the order can return, but often in a new, random direction. These aren't just metaphors. They're mathematical cousins to the process in quantum field theory. In each case, you have a field, like the alignment of atomic magnets or the arrangement of water molecules sitting in one configuration. An external factor, like temperature or a seed, provides the nudge to push it over an energy barrier into a more stable configuration. The change then propagates outward from that nucleation point, transforming the entire domain. Vacuum decay is this same physics, scaled up to encompass everything. The Higgs field is like that alignment, or that arrangement of water molecules. Our universe is that supercooled liquid, or that magnet just below its Curie point, stable for now, but not in its absolute lowest energy state. A quantum fluctuation in deep space acts like that speck of dust, that final degree of heat. It provides the nucleation site, and the new configuration of the Higgs field, the true vacuum, spreads out from that point at light speed, rewriting the cosmic order just as ice rewrites the structure of water. This connection is deeply comforting to a physicist. It means the terrifying idea of a universe deleting itself isn't a bizarre, one-off fantasy. It's an extension of well-understood principles. The spontaneous rearrangement of a system's ground state is a cornerstone of condensed matter physics. We study it, we manipulate it, we use it in technology. The existential twist is only one of scale and consequence. In the lab, a phase transition changes a material's properties. In the cosmos, it would change the very rules that allow materials to exist. The analogy grounds the unthinkable in the familiar. It tells us we're not imagining monsters, but recognizing a pattern. A pattern written into the fabric of reality at every level. The universe may operate by a consistent logic, whether in the formation of a snowflake or the potential fate of a galaxy. And in that consistency, there is a strange and formidable beauty. There's a paradox inside that kind of beauty. If a bubble of new physics replaced our universe, what happens to all the information it ever held? Not just files on a drive, the fundamental record of everything that ever was. Every supernova, every mountain, every thought. In our current physics, information isn't truly lost. You could burn a book to ash, and the information about its pages is still there, scrambled into the radiation and the smoke. With infinite knowledge, you could reverse it. Reconstruct it. A black hole poses a version of this puzzle, but most physicists think the information is preserved there too, just hidden, incredibly hard to reach. The event horizon conceals it, but it doesn't delete it. A vacuum decay bubble is different, more absolute. It doesn't hide information behind a horizon. It destroys the medium that could store it. Because information, in the physics sense, is a particular arrangement of particles of forces, it needs a stable framework. A memory is a pattern of neural connections. A book is ink arranged on paper made of specific molecules. Starlight is encoded in photons with precise energies. All of that depends on the laws of physics staying consistent. If those laws change at a fundamental level, if protons decay instantly, if the forces that bind atoms vanish, then the patterns dissolve. Not into simpler parts, into a new reality where those parts and their arrangements have no meaning. It would be like trying to preserve a novel written in English by translating it into a language where the words for character and plot and page don't exist. The translation isn't just poor, it's impossible. The concepts themselves have no counterpart. In the new vacuum, the alphabet of reality is different. The particles, the forces, the constants, they are a new set of symbols. The epic story of our cosmos, written in the old alphabet, becomes literal nonsense. It isn't stored in some inaccessible vault. It's rendered physically incoherent, and that opens a kind of philosophical abyss, beyond any astronomical catastrophe. It challenges the idea of a permanent past. We take for granted that what happened, happened, that the Battle of Hastings was in 1066, that dinosaurs walked the earth. That your first memory is a real event anchored in history. These are facts of the cosmos, but if the universe's operating system is overwritten, are those facts still true? In a cosmos where the structures that evidence those events can no longer even be described, in what sense did they ever occur? It's a finality more complete than any black hole's silence. An event horizon at least preserves the information, even if we can't reach it. This would be the deletion of the ledger itself. The implications for legacy are staggering. Every act of creation, every struggle, every discovery not just lost to time, but to the very fabric of causality. It would mean that nothing, in the end, was written in stone. Because the stone itself would cease to be stone. This isn't pessimism, it's a logical extreme. It forces us to examine why we value permanence in the first place. Our drive to build, to record, to remember, it assumes a future that can look back. A vacuum decay event severs that thread, not just for us, but for all potential future observers. It resets the cosmic clock to a blank state, with no memory of what came before. Yet, inside this thought experiment, there might be a sliver of perspective. If our universe is one bubble in a multiverse, then while information is annihilated inside our bubble, the fact of our bubble's existence, that it formed, that it lasted, that it contained a rich history, could be a permanent fact in the wider multiverse. Our entire cosmos, with all its information, becomes a single data point in a higher dimensional history. The story isn't readable from inside after the change. But from the outside, the story of the bubble's life and death is part of a larger, enduring narrative. Our legacy, in the most cosmic sense, might not be in preserving the pages, but in having been a chapter that was once written. The terror of absolute erasure meets the consolation of a witness, somewhere in the grand architecture of reality. That question of legacy, of being a chapter in a larger story, leads to another. If intelligence is the universe understanding itself, could that intelligence ever learn to protect its own chapter? Could a civilization not just survive, but defend itself against a cosmic rewrite? That's a question for a far future. A civilization that's mastered not a planet or a star, but the energy of an entire galaxy. A Type 3 civilization. For beings like that, the universe isn't just a home, it's a project, a system to be understood and maybe maintained. Their first task would be detection. Could they see it coming? The nucleation of a true vacuum bubble is a quantum event. It's random and sudden, but on a cosmic timescale, maybe it's not entirely unpredictable. There could be precursor signals, subtle fluctuations in the quantum foam, but on a galactic scale. A faint statistical whisper in the background of space itself. A hint of a region where the energy barrier is growing thin. A civilization that has mapped the Higgs field across millions of light years, monitoring its stability like a heartbeat, might spot a dangerous anomaly long before it tunnels. They wouldn't have a warning of days or years. They might have millennia or eons, enough time maybe to act. And what could that action be? One speculative idea is local stabilization. Could they engineer a fix? Pour immense energy into reinforcing the false vacuum state in their region of space. Think of it as cosmic structural engineering. They might create a vast scaffold of energy fields, a bubble within a bubble artificially propping up the Higgs value, making that local energy valley deeper, more stable. It would be the ultimate preservation project, a museum of physics maintained at a staggering cost, protecting their galactic home from the changing laws outside. Or maybe their strategy would be mobility, not fortification. A life raft. They might learn to construct a self-contained region of space, a vessel trillions of kilometers across that artificially simulates the old false vacuum physics inside its boundaries. This arc would then detach, moving through the new, alien vacuum outside like a submarine through an ocean of different physics. The survival of their entire civilization, its culture and knowledge, would depend on keeping this impossibly complex bubble of familiar reality intact. Against the pressure of a fundamentally different cosmos, it would be the greatest engineering feat imaginable, a testament to a will to endure that spans the life and death of universes. These are dreams, of course, at the very edge of science. They border on mythology, but they serve a purpose. They reframe vacuum decay from an absolute, impersonal end into a potential challenge. The ultimate challenge for intelligence. It asks whether consciousness, having emerged from the laws of physics, could ever reach back and secure those laws against their own instability. In this light, our own scientific inquiry today is the first step on that long road. We are not just passive residents in a cosmos that could change its mind. We are the early ancestors of a process that might one day learn to read the cosmic fine print, and maybe, just maybe, negotiate its terms. That long road starts with something much simpler, just looking. Could we find evidence this has happened somewhere else with the telescopes we have now? The answer is yes, cautiously. It turns a philosophical fear into an astronomical puzzle. You'd be hunting for the scars a bubble leaves behind. Picture a sphere of true vacuum, expanding at light speed for billions of years. What would it leave behind? From far away, we wouldn't see the change in physics itself. We'd see what it does to the structures we can actually observe. The biggest sign might be a perfect, spherical void in the large-scale structure of the universe. Inside that void, the rules for making galaxies would have stopped working long ago. When the bubble wall passes through a region, it doesn't destroy galaxies like an explosion. It just makes the physics that lets galaxies shine and hold together stop. The stars in those galaxies would wink out, not with a bang, but as their atomic bonds dissolve. The gas clouds that would form new stars become inert, just elemental soup. From where we are, we might see a vast, dark sphere in space where the density of galaxies drops abruptly to zero. A perfect circle of nothing, expanding over cosmic time, its edge sharp against the web of galaxies around it. Finding something like that in galaxy surveys would be like finding a hole punched in a tapestry, a hole that gets bigger the further back in time you look. There's another, more subtle clue. It could be etched into the oldest light we see, the cosmic microwave background. That faint glow is the afterimage of the early universe. If our expanding universe ever collided with a bubble of true vacuum from somewhere else, the shock of that collision would leave a mark. It might show up as a strange, circular pattern of temperature variations. A cold spot or a hot spot with a perfectly sharp edge, like a bruise on the sky from an impact with a different reality. Astronomers have actually found a few anomalous cold spots in the microwave background. They are larger and colder than our standard models predict. They're almost certainly explained by cosmic variance or other complex physics, but for a moment they let you wonder. Could one be a fossilized collision? The search means sifting through petabytes of sky data, looking for a pattern that defies all the standard explanations. A single, perfect circle of altered physics on the most immense canvas imaginable. That changes the threat completely. Vacuum decay isn't just a theoretical risk anymore. It becomes a possible source of discovery. It gives astronomers and cosmologists a bizarre, faint signature to hunt for. They're already mapping the universe in incredible detail, charting billions of galaxies, measuring the microwave background with extreme precision. Inside those vast datasets, they are looking for anything that doesn't fit. The signature of a vacuum decay event would be the ultimate outlier, a message from a neighboring cosmos or a relic from our own past, written in the language of missing galaxies and distorted ancient light. It's a needle in a haystack search on a cosmic scale, but the mere possibility reframes the whole idea. We're not just potential victims of a silent erasure. We're detectives scanning the sky for clues that the laws of physics aren't just local, that they might have neighbors, and in that search, even finding nothing becomes meaningful data. A hint that our cosmic neighborhood might be more stable and more isolated than we ever guessed. Looking for these silent scars in the sky is one thing. Living with the possibility is something else. This idea that the universe could in principle rewrite itself without any warning, it settles into the mind in strange ways. It's the ultimate sword of Damocles, but hanging over all of reality, held up by a fraying thread of quantum probability. For some people, the whole thing is just too abstract, too distant to really feel. It's a curious footnote from physics, interesting but with no emotional weight. The concerns of daily life are far more immediate. They're more real. For others, though, it can trigger a deep unease, a kind of cosmic anxiety. It's the feeling that the ground of existence isn't solid. That everything we've ever done, all the art, the love, the memory, it all rests on a foundation that might, against all odds, just cease to be valid. Philosophers and psychologists have long asked how we process risks this vast and impersonal. The ancient Stoics, they practiced thinking about the cosmos, the brevity of life. They did it not to create despair, but to find tranquility. By seeing how small and temporary our concerns were in the grand scheme, they tried to free themselves from petty worries. Today, understanding vacuum decay can serve a similar purpose, a more extreme one. It frames all human strife, our conflicts, our ambitions, our personal fears, against a backdrop of such staggering scale and potential fragility that it can actually shrink them. Our daily troubles don't disappear, but they are placed in a new perspective, a humbling one. This isn't nihilism, it's a recalibration of value. The psychologist William James wrote about the moral equivalent of war, a cause that could inspire human effort without destruction. Confronting the fragility of physical law might be the cosmic equivalent. It shows that the stability we have, the laws that let planets form and minds think, it's not a guaranteed default. It's temporary, it's precious, it's an astonishingly improbable arrangement. Knowing it could be otherwise, even in theory, it sharpens your appreciation for the fact that it is. Right now, for us, that awareness can be liberating. It says the stage we live on isn't a permanent, indifferent prison. It's a rare garden, a fleeting one. The very contingency of reality, that it might not have been this way and may not always be. It makes this moment of coherence and consciousness not a given. It makes it a gift. The universe didn't have to be understandable or beautiful or capable of harboring life, but here we are, in a pocket of spacetime where it is all those things. That theoretical sword above reminds us not to take the ground for granted. It invites a shift, from anxiety to a kind of grounded gratitude. Our time here, and the stability that allows it, that's the real marvel. Not its potential end. So every moment of curiosity, every connection, every act of creation becomes a quiet celebration, a testament to the temporary, glorious stability we are here to witness. That feeling of gratitude for our brief moment here, it connects to something very old in us. For as long as people have looked up at the stars, we've told stories about the end of the world. And in those stories, the end is never really the end. It's more like turning a page. The Norse had Ragnarök, a great battle, gods and giants falling, the world burned and then drowned. But from that, a new, green earth would rise, a new generation of gods, so destruction was a necessary step, a precursor to rebirth. Hindu cosmology sees time in these vast cycles, kalpas. Each one is a day for the creator god Brahma. It lasts over 4 billion of our years, and at the end of that day, the universe dissolves, goes back to an unmanifest state. Then the next day dawns and it's created again. An endless rhythm, manifestation, and then rest. These aren't just stories about doom. They're narratives that put our existence inside a grand, cyclical process. They give cosmic endings a purpose, a clearing of the slate, so something new can begin, and there's a parallel there, with the most modern scientific view of vacuum decay. In the multiverse picture, a bubble of true vacuum, it doesn't just erase a universe. It spawns a new one. The energy from that transition, it fuels a new Big Bang. New inflation, a new cosmos with its own laws. Our universe might be the child of such an event, from some older reality, and ours might one day give birth to others. The scientific story, without the gods and giants, it arrives at the same archetype. The cosmic cycle, death and rebirth, but not of life, of reality itself. That connection is profound. It suggests the human mind, through myth and now through science, has been circling the same truth. We've always sensed this stage we're on isn't permanent. That it had a beginning and will have an end. But we've also intuited the story is larger, bigger than our single act. The ancient myths personified these forces, gave them faces, motives, gods of chaos, of order, creation, destruction. Modern science quantifies them, gives us equations for inflation, for quantum tunneling, for the Higgs potential. But the underlying melody, it's the same. Transformation on the ultimate scale. So the unsettling idea of vacuum decay, it's part of a timeless human tradition. We're not the first generation to stare into the abyss of cosmic finality. We're just the first to do it with telescopes and particle colliders. Our evidence-informed mythology of cosmic inflation. Metastable vacua, it continues a conversation that started around campfires. It's a new chapter in the oldest story we know, the story of where we are, and what might lie beyond the horizon of our own reality. In that light, science doesn't strip wonder or meaning from the cosmos. It gives us a new set of images, deeply awe-inspiring images, for the same eternal themes. The cycle continues, not just out in the stars, but in our endless quest to understand them. But that mystery has a clear edge. Our understanding of vacuum decay pushes right up to the limit of what physics can tell us now. It sits at this intersection, where quantum field theory meets the unknown of quantum gravity. A place where our equations, they work so well in other places, but here they start to break down. We can outline the landscape, but we can't reliably calculate the odds of a tunnel without a complete theory. A theory that unifies all the forces, including gravity, at the smallest scales. And that theory, it doesn't exist yet. So those haunting probabilities, the Googol-Year timescales, they come with this silent asterisk. They are our best estimates, but from an incomplete map. This uncertainty, it isn't a failure, it's the heartbeat of science. The possibility of vacuum decay, however remote, it stands as a reminder. Our understanding of the cosmos is provisional. It's a snapshot. It's always being developed. The universe, in its depth, it might hold configurations, behaviors that we can't even imagine yet. Surprises written into reality that our models haven't described. This humility is central. It tells us the final word on cosmic stability isn't in every puzzling calculation, every theoretical limit. It's not a wall. It's a signpost, pointing to the next frontier. The mystery itself, this blend of mathematical warning and deep uncertainty, it's what drives the search for a deeper theory. It means our story of the universe is never finished. There are always new chapters, written in a language we're still learning to read. We end without an answer. We end with a different question. We've been at the edge of physics, looking at something so absolute it changes what fragility means. The vacuum decay bubble. It's not just a cosmic eraser. It's a mirror. It shows how contingent everything is, all of it. The probabilities are tiny. The timescales are longer than any story. But the possibility is there. It's in the equations, and that forces a kind of confrontation. It makes you look at the ground, at the stars, and you see it all as temporary. A specific arrangement, a configuration of fields and forces. It didn't have to be this way, and that realization, it doesn't have to be fear. It can be a deeper wonder. The universe holds a beauty that includes the potential for its own silent change. We are here, conscious, curious, inside that window of stability. That's the marvel. Our search for understanding, from myths to colliders, it's the universe starting to know itself. That quest doesn't end. It moves to the next horizon. The next puzzle in the fabric of reality.